Advanced jet engines utilize complex shielding to maintain reliability during adverse conditions and sudden mechanical stressors.
Protective protocols ensure that internal damage is minimized, preventing total component failure and expensive overhauls.
Having analyzed surge prevention and generator safety, we now explore deeper system-wide protective mechanisms.
The automatic ignition circuit activates when combustion stability is threatened by heavy rain or ice intake. Electronic monitoring detects rapid RPM loss, immediately firing the igniters to re-establish continuous engine thrust.
Once the flame is restored and rotation stabilizes, the system resets to preserve the igniter's lifespan. The engine's lubrication network is critical, cooling and protecting 6 main bearings and the accessory gearbox.
Front-end bearings support the low-pressure shaft, while mid-section ball bearings stabilize the high-pressure core assembly.
Roller bearings in the rear handle radial loads, ensuring the turbine shafts remain perfectly aligned under stress.
Precision-machined ball bearings manage axial thrust, absorbing the massive forward force generated during takeoff power. Oil is pressurized by the gearbox pump, flowing through heat exchangers to regulate temperature before distribution.
In the heat exchanger, thermal energy transfers from the hot oil to the cold fuel, increasing combustion efficiency.
After lubricating the core, the scavenge system retrieves the oil, filtering it for debris before returning to the tank. External core cooling prevents thermal soakback, protecting sensitive electronics and gaskets from extreme engine temperatures.
A dedicated valve directs cool bypass air around the engine casing, creating a thermal shield for internal components.
Fire detection loops are the final line of defense, monitoring the engine nacelle for localized heat spikes. Dual loop systems prevent false alarms, requiring both sensors to confirm a fire before alerting the flight deck. When the fire handle is pulled, the fuel, hydraulic, and bleed air valves are instantly sealed shut. Extinguishing agents are released from high-pressure bottles located in the aircraft's cargo bay through dedicated lines. These systems ensure that even in a critical emergency, the aircraft remains controllable and the fire is contained. Beyond internal cooling, the GE90 utilizes mechanical safeguards like the thrust reverser tertiary locks.
The transcowl sleeves slide aft, exposing cascades that redirect fan airflow forward to assist braking.
Multiple independent locking mechanisms prevent accidental deployment during high-speed cruise or takeoff phases.
Real-time vibration monitoring uses piezoelectric sensors to detect infinitesimal imbalances in the rotating shafts. Data is processed instantly, alerting the crew if mechanical wear exceeds predefined safety thresholds.
Exhaust gas temperature, or EGT, is monitored at the turbine exit to ensure thermal integrity.
If temperatures approach redline limits, the control system automatically modulates fuel flow to protect blades. Anti-ice systems utilize hot bleed air to prevent ice buildup on the engine's leading edges.
The intake cowl and the spinner are heated to maintain aerodynamic efficiency in freezing altitudes.
These layered systems work in harmony to ensure the GE90 operates safely across the global flight envelope.
At the heart of engine management is the FADEC, providing dual-channel redundant control logic. This digital brain cross-checks sensor inputs, ensuring that a single failure cannot compromise thrust. FADEC controls the fuel metering unit, optimizing the mixture for every altitude and temperature. It also manages the variable stator vanes, adjusting blade angles to prevent compressor stalls. Active clearance control regulates the gap between turbine tips and the casing for maximum power. Constructed of high-strength Kevlar and steel, this shield protects the aircraft fuselage and passengers. Advanced surge recovery logic detects pressure reversals, instantly opening bleed valves to stabilize flow.
This prevents structural damage during extreme maneuvers or sudden atmospheric pressure changes.
Every parameter is recorded, feeding the aircraft's health management system for predictive maintenance. Modern sensors track component life cycles, allowing for parts to be replaced before they fail.
This transition from reactive to proactive maintenance has revolutionized commercial aviation safety. During the descent and landing phase, the FADEC ensures smooth throttle response for precision control.
During the descent and landing phase, the FADEC ensures smooth throttle response for precision control.
Even at idle power, the engine maintains enough core speed to power all aircraft systems.
Backup generators and hydraulic pumps remain online, driven by the rotating accessory gearbox. If an overspeed event occurs, the mechanical fuel shutoff provides a final, unhackable physical safety.
Thousands of flight hours are logged annually, proving the reliability of these complex protective architectures. From ice-cold Arctic skies to the humid tropics, the GE90 remains a masterpiece of engineering.
Understanding these systems gives us a glimpse into the future of ultra-efficient and safe propulsion. Join us in the next episode as we push this incredible engine to its absolute performance limits.